Let's look at logarithms of a complex number to the power of complex number. Let's see what I mean by that. So let's say we have a number a to the power of z. Okay, here a and z are both belonging to real numbers. Okay, what we can do is we can write it as e to the power of log e of a to the power of z. Yes, we can do this because e and log are inverses of each other. We can do this. Okay, so this is nothing but az. They are equivalent. Or we can, based on log rules, we can bring the z down. So e to the power of z log e of a. Similarly, when it comes to a complex number to the power of complex number, we can write the same thing. So a to the power of z is equal to e to the power of z log e a, where a and z belong to complex numbers. Now, in general, log e of a is equal to 2n pi I plus log e of a, right? This we know. So which means similarly a to the power of z is equal to e to the power of z 2n pi I plus log e a. This would be the general form, which means a to the power of z is a many valued function. Now, one of the things that we have noticed is that, we should be in a position to separate out the real and imaginary parts. So let's see how we can separate the real and imaginary parts of a log of a complex number to the power of complex number. So a plus ib to the power of x plus iy. We want to split it into two, one real and one imaginary, which means this can be written as e to the power of x plus iy log e of a plus ib, right? In here we were just writing a to the power of z. Here we are writing the actual complex number itself, and here you have to follow a little bit carefully. In general, what will it be? X plus iy 2n pi I plus log e of a plus ib. I just added the 2n pi I part. Now we know that log e of a complex number is equal to half of log e of a square plus b square plus I tan inverse of b by a. We know this. So let's simplify it, because every time I don't want to keep writing this entire thing. So let's say this is a plus ib. So here a is this, b is this. So which means we can write a plus ib to the power of x plus iy as e to the power of x plus iy times 2n pi I plus a plus ib. So I substituted this with this e to the power of x plus iy, and this we can take the common, like terms, we can group them. So I 2n pi plus b plus a e to the power of, now let's multiply both. Okay, what do we get? We get x times I 2 n pi plus b plus ax plus I square y 2n pi plus b plus aiy, right? This entire thing is the exponent. E to the power of, so this will become minus I square, okay? And let's see, xi 2n pi plus bxi plus ax minus 2n pi y minus by plus aiy. Again, this entire thing is the exponent. E to the power of those terms which are not I. So ax minus 2n pi y minus by plus aiy, and then we have plus I times 2n pi x plus bx. It is a little bit tricky. Now here aiy also contains I, so it should go inside this because that also has I common. So ay. Things seem to be looking up, right? Now here we can take this and we can take this, right? Like this, we can separate it out. Now there is a plus sign here. I don't have to put a sign on both the sides, both places. Okay, so since plus is there on an exponent, we can split it into e to the power of ax minus 2n pi y minus by times e to the power of I 2n pi x plus bx plus ay. Okay, now remember e to the power of I theta, this entire thing we can treat it as theta. So which means we can write it in another form. So e to the power of ax minus, here y is common, so 2n pi plus by, and e to the power of I theta can be written as cos theta plus I sin theta. So cos of 2n pi x is common, so let's take it together. So cos of 2n pi plus bx plus ay plus I sin theta, that is 2n pi plus bx plus ay. Okay, now here let me write it again, uh, because ideally it should be in single line so that you can see what is exponent, what is. So here what do we have? E to the power of ax minus 2n pi plus by, and that is the end of the exponent, multiplied by cos 2n pi plus b plus ay plus I sin 2n pi plus b x plus ay. And here remember, a is equal to half of log e of a square plus b square, right? A. So all those places we have to actually put this value. Okay, and b is equal to tan inverse of b by. So we have seen how we can represent log of a complex number to the power of complex number, and we have seen how we can separate the real and the imaginary part. That's it. Bye.